still talking about the appendix. But you need to know this stuff so that you can understand where the solutions to the discussion, the problems, the DEs in angular momentum come from. Okay. Now this generator for the associated Legendre polynomials, that's for the case when m is non-negative, positive or zero. Right? Now there's an equivalent form. If you know the positive, for positive m or zero or non-negative m's, there's an equivalent form which is of this form when m is negative. Okay, so you take when m so m's negatives. So this would give you your positive. That would then make m minus m positive, right? And just multiply it by this term, and that will give you the corresponding value for the associated Legendre polynomial, this, when m is negative. Okay. Now there is restrictions on the value of m, like the Legendre polynomials, not the associated Legendre polynomials, but just the Legendre polynomials, P of L, with just one parameter L. That's a polynomial with a limit, an upper limit to the order of, well, the degree, like the degree. So PL is a polynomial of degree L. So the highest power of x in this polynomial would be L, right? X to the L. That's the highest power. So you cannot differentiate too many times, right? Because if you do, you just get zero, and then all your polynomials are zero. So there's a limit to how many. The limit to m. And if you think about it, if PL, if its order is L, you can't differentiate it more times than that. Okay. So m is less or equal to L. Now m can take negative values as well. So m. Well, that may not be so obvious. Well, there are various clues. For example, say m is larger than L. Imagine m is larger than L. Well, then you get a negative factorial. So that sort of makes you suspicious. And also, if you're differentiating more times than L here, that'll give you zero. So you've got a limit on m. So your m here is less or equal to L and greater or equal to minus L. So your m is limited, right? It depends on L. All right. Now we come now we come to a critical moment in angular momentum theory, because somebody, I guess, where would it have been? 1920s, 1930s, I guess. Somebody must have made the momentous discovery that angular momentum theory, quantum mechanics, links up with the associated Legendre polynomial and equation, associated Legendre equation. So I've asked you, homework. I've asked you to do this as homework. So if here. So if this polynomial here, the Legendre polynomial, if it satisfies, it's a solution to, in other words, if it's a solution to, if it satisfies Legendre's equation, which we wrote out in an earlier session, okay, then the associated Legendre polynomial with two parameters, ML, satisfies the associated Legendre equation. Now, the textbook was a little ambiguous. I'm not quite sure what this P, does this P refer to this or to this? So, I haven't thought that through, but think about it, right? So, what is this P? But this is the associated Legendre equation, okay? Oh, okay, it's this, it says so, right? Then this satisfies this equation. So this P here is this. you're assuming that P of L satisfies the Legendre equation, and therefore this associated Legendre polynomial satisfies the associated Legendre equation. Okay, so prove that. With one simplification, you're assuming that H bar is 1. Okay, so new thought. The double bar just means separate one topic from the next one. I could go into a new line, but I try to make things fairly dense. Given the upload time is hours to YouTube is hours per session, I don't want to waste space. If I waste space, that means wasting time. So the necessity of the YouTube situation demands compactness, denseness in the writing on the whiteboard. Okay, I hope you appreciate that. Okay. Now these associated Legendre polynomials, they actually form an orthogonal set, and you can normalize them as well, and hence you can get by pre-multiplying, by multiplying by a certain normalization factor, some constant, you can generate from these associated Legendre polynomials, you can generate an orthonormal set, right, which you can use as a basis for some wave function, if you like, connected with angular momentum, right? Now again, it's just thrown at you. You're not expected to be specialists in differential equations on this stuff. Just giving you the information. So now this value here for these associated Legendre polynomials, they range over plus or minus 1, like cos theta. The maximum value of cosine is 1, minimum value is minus 1. So the range here, it's not minus infinity to plus infinity, it's just minus 1 to 1. Okay, and you take the product of two of them, and what's different? Oh, for the same m, but different L's. Okay, L dashed and L. So with the same m and different L's, you get this expression. And here's your Kronecker delta, delta L dashed. So in other words, if L and L dashed are different, if they're different integers, this expression is 0. Okay, so if L and L dash different, but with the same m, constraint, these two associated Legendre polynomials are orthogonal if L dash and L are different, right? Due to this. And if they're equal, then that becomes 1, and you get this. Now you can multiply. It's the next line of the next session, but I can just tell you. If you multiply this Legendre polynomial by 1 over the square root of this, then you normalize that polynomial. Okay, because then you just get 1 here, right? Also normalized. Okay, so until the next session.